Alrighty, in this video we are looking at one of my personal favorite functions, logarithmic functions. Our objectives are to convert between exponential and logarithmic form, to evaluate logarithmic expressions, and in a little bit later we'll actually graph them as well. So I want us to take a look at this graph. Really, we have two different equations graphed here. The red graph is the exponential function y equals 2 to the x. We've been studying exponential functions, and this is an exponential growth function, and its b value, its rate is 2. And so it's going to have, it's approaching that x-axis, not actually touching it, and then it's going to be growing and growing and growing as you go to the right. What you see reflected across that dotted line is the inverse. The blue graph is the inverse of that particular exponential function. We've also studied inverses, so you'll see that they have that nice symmetry across the line there, that dashed line, and because they are inverses, we can compare their x and y values. At -2 for our exponential function, the red graph, it's 1/4 or 0.25. At -1, it's 1/2. At 0, the output's 1. At 1, it's 2. And at 2, the output is 4. You can check those. They're all plotted there on that graph. Now, similarly, I want to show you the points for that blue graph, for the inverse. Remember, an inverse graph, the domain and range are just going to flip. So at 0.25, the output is -2. At 0.5, the output is -1. At 1, it's 0. At 2, it's 1. And at 4, the output is 2. You can see that side by side how we have interchanged. We've flipped the x and y. We've switched those values. Their graphs are symmetrical across that line. Now, what I want to do is actually find the equation that models that blue function, because we know how to find those as well. If we wanted to find the inverse of this exponential function, the first thing you would want to do is interchange the variables. So that's our function. You'd want to write it with the y variable instead of f of x, and then you'd flip x and y. Then we would need to solve for y. And how would we do that? You can't just divide or multiply or add or subtract. You can't even take a root. We currently do not have a method, a means by which to do this. Up until this point, all the information that you have acquired does not allow you to actually solve for y, which I know makes you feel like this. But ladies and gentlemen, there is a mathematical invention here to rescue us. We have defined the inverse for exponential functions as logarithmic functions. So your function, f of x equaling log b of x, little stipulation here, b has to be greater than 0. It cannot be 0, and x is also going to need to be positive. That function is the inverse of the exponential function f of x equals b to the x power. So there you have it. When you're working with exponential functions and trying to find their inverses, we have to use this defined idea of logarithms. Now let me give you a little bit better look into this. Logarithms, get it? Log. If you are working with the logarithm of x in base, I'm sorry, that's actually supposed to be b. Will you change that? In base b equals y, that would be written like this. Log b, logarithm of x in base b equals y. That is how you would write that. And what a logarithm is actually, it's actually kind of a question. The question that a log is asking is, what exponent must we raise b to the power of to yield x? Let me contrast and compare the forms of exponential and logarithmic here. The base in the exponent, in the exponential form, is the base of your logarithm. The output there, the y, is the exponent. And that's what you're trying to find in the logarithmic form, because if you recall, if you look back, it was when we were trying to find the inverse, we didn't know that y, we couldn't isolate for y. What we're trying to do is find the exponent that would give us that x value. So this could seem very perplexing. Okay, well, how do I find that? There's a means by which I want to show you. There's kind of like a trick, and I mentioned it in class. You kind of have to do a backflip, but I promise it's easier than actually doing a backflip. So if you have your log, and it's written in log form, and you want to convert it to exponential form because that's something we understand better. This log of x base b equaling y, you want to think about it like this. What base, what would we raise, b raised to what power, I guess is the right way to say that, b raised to what power, because it's the y value that we don't know, equals x. That would be written exponentially, b raised to the y power equals x. So looking at this next problem, there's actual values here, and so we're going to think through this like we did just above. 4 raised to what power equals 64? I would write that out. 4 raised to y equals 64. And now this is kind of a puzzle. Okay, well, what would I raise 4 to the power of to give me 64? I'll give you all a moment to maybe think that through. You might be able to do that mentally or check it with a calculator. That value is 3. Your y value is 3 because 4 times 4 is 16 and 16 times 4 is 64. So the answer to our problem, log of 64 base 4, is 3. This little, well, let me take a moment here to say this. Always draw your loop counterclockwise from the subscript, from your base. You always want to start at your base and go counterclockwise. Otherwise, that's how the trick works. Okay? This trick also works if you're given exponential form and you want to convert it to logarithmic form. That's one of our objectives. So it's a nice multi-purpose tool, you could think of it. So log base A of x equals y. That would be written out like this. Log the A, remember, that's going to be down in the base position of x, and what we're trying to find is the exponent, the y value. So this one down here, the next example, we would read this as log base 7 of 343 gives us x. Okay,